In this lecture, we'll talk about physical properties, and our reference is Richard Lenart from page 37 to 44. We will include rheological properties, and rheology is the study of the flow of material. It involves mixing the material to produce liquid or dough that is suitable for the patient's need. Therefore, it is really important to understand the rheology of the materials. Then we have thermal properties. Thermal properties is also important. Now the temperature in your mouth is 37 degrees Celsius, and it can vary from 5 to 60 degrees Celsius according to what you eat. For example, when you drink a cup of tea or eat an ice cream, the temperature will change. And this change in temperature may irritate your pulp, so it's really important to protect the pulp from these thermal changes. Liquid flow is measured by viscosity, and solid flow is measured by creep and viscoelasticity. Viscosity is the resistance to flow, and to understand it better, let us take an example, the water. The force that bind the molecule together are very weak. That's why it has low viscosity. When the force that bind the molecule together are high, the material will be highly viscous. We have here two formulas, and to understand these formulas, we will move to the next slide which has the figure. Here we have a container with liquid, and on top we have a plate. When you apply force, it will develop stress, and the stress is called shear stress, which will make the plate move. The degree of the stress is quantified by the shear rate. The shear rate is the change of velocity at which one layer of fluid passes over an adjacent layer. From here we will get the two important formulas, which is the shear stress is equal to the force over the area, and the shear rate is the velocity over the distance. When you measure the shear stress over a range of shear rates for a fluid, you will have this constant linear relationship for many fluids. And this slope is equal to the velocity. The material that has this relationship is said to have Newtonian behavior. Not all liquids behave in the Newtonian behavior as in the previous curve. We have plastic behavior. In the plastic behavior, the material will not flow until the initial shear stress have been reached. After that, it will flow in the Newtonian way. Then we have dilatant liquid. In the dilatant liquid, as the shear rate goes up, the viscosity will increase. This means the faster that you mix the fluid, the more difficult the fluid becomes. And the opposite is true for the zetoplastic. In the zetoplastic, an increase in the shear rate does not lead to a corresponding increase in the shear stress. So, the faster that you mix the fluid, the easier the mix will become. Acrylic resins behave as a dilatant liquid. Polyether impression behave as a zetoplastic liquid. Thixotropic behavior occur when mixing the material, the molecules change their places, and when they didn't have enough time to return back to their original place, thixotropy will occur. The viscosity of the fluid is dependent on the previous deformation it was subjected to. And from the curve, you can get the definition of thixotropy. It is the viscosity for an increasing shear rate is different from the viscosity for a decreasing shear rate. An example of this is ketchup and non-drip paint. Viscoelasticity is of two terms, viscosity and elasticity. In viscosity, the material will not return back to its original shape. Elasticity, the material is able to return back to its original shape after the removal of the force. Here we have three behaviors. The first one, the spring. The spring represents the elasticity. When you apply load to the spring, there will be an immediate strain, and it will be maintained as long as you're holding the load. Once you remove the load, the spring will return back to its original position. Then we have the dashpot. The dashpot represents the viscosity. When you apply load to the dashpot, there will be a gradual increase in the strain, and it will gradually increase as long as you're holding the load. Once you remove the load, the dashpot will be maintained in the new position. Finally, combining both of them together, the spring and the dashpot, we will get the viscoelastic behavior. Now the dashpot here will act as a ruler, and it will prevent the spring from reacting elastically. On the removal of the load, the dashpot will prevent the spring from contracting to the unstrained state, but it will be achieved after some time. Some examples of viscoelastic dental materials are elastomeric and hydrocolloid impression material and dental amalgam. Now, viscoelastic behavior depends, as we mentioned, depends on the time and the rate of deformation. If they deformed rapidly, it will behave elastically, and this will make the material stronger, and the opposite is true. The material that will conduct heat is a thermal conductor, and the material that will resist the conduction of heat is a thermal insulator. When you heat a material, there will be extra energy, and this will cause thermal expansion. Thermal conductivity determines the ease with which the heat is transferred through a material. It's represented by K, and it's the rate of heat flow per unit temperature gradient. Specific heat is the heat energy required to raise the temperature of a unit volume by 1 degree centigrade. It indicates how rapidly the material heats up. When material transfer from hot or cold, it depends on two things: thermal conductivity, which regulates the rate at which heat enters and passes through, and thermal diffusivity, which determines the rate at which temperature will rise. It is represented by H. The water is a perfect insulator because it has a very low thermal diffusivity. When you want to measure the thermal expansion of a material, bring 1 unit length of the material and heat it for 1 degree centigrade. The resultant change is the linear coefficient of thermal expansion, which is represented by alpha. It is very small, that the unit is parts per million per degree centigrade. The following table shows the coefficient of thermal expansion of the tooth structure as well as some dental material. Ideally, it should have the same coefficient of thermal expansion of the tooth structure. Otherwise, marginal gap may occur. So you can see that the enamel has 12, dentine has 14, porcelain 12, so it's the same as the tooth structure. You can also see that the GIC is very close, it is 8. And you can see that the resin composite varies from 20 to 55 according to the filler content. Fissure sealant is 8 times the enamel. As we mentioned earlier, when two materials bond together, they should have equal coefficient of thermal expansion. An example is metal and ceramic. Or otherwise, there will be bond failure.